So to set up our discussion of magnetic flux, let's step back and talk about an idea that probably makes a little more intuitive sense to you, and that's an idea that we might call air flux. So air flux is a measure of how much air flows through a window. That's going to depend on three things. The first one is how windy it is. So obviously you're going to get more air flux, so more air will come through the window on a windier day than on a day where there's not much wind. Second thing, of course, is what's the size of the window? The bigger the window is, the bigger you would expect the air flux to be. So those first two factors probably make a lot of sense. The third thing that matters is which direction is the wind blowing. So think about two scenarios. In the picture on the left, the wind is blowing directly into the window. The picture on the right, however, is a situation where the wind, in whatever way we make this happen, is now blowing basically up the wall. So instead of blowing into the window, it's blowing past the window. And so I think what you would recognize is that I've got the same size window, I've got the same wind, but the fact that this one is blowing along the window rather than through the window means that I'm going to have a lot less air flux in this picture on the left. So that's the third thing that really matters in terms of thinking about the air flux. So we can rename these three factors and call the first one, instead of how windy it is, what's the strength of the wind? The second one is what's the area of the window. And the third one we're going to relabel as the relative orientation of the wind and the window. So what's the relative direction of how the wind is blowing relative to how the window is sitting? Well, magnetic flux is a very similar idea. It's just instead of thinking about wind flowing through a surface, we're going to think about how much a magnetic field flows through a surface. So if you look at our picture down here, these lines we were using to represent the wind, well, now we're using them to represent the magnetic field. So I've drawn in red these magnetic field lines, and I still have a surface here that has some area. And so I can think about the magnetic flux through this surface, and that's going to depend on three things. The first one is, what's the strength of the magnetic field? That should sound familiar. The second one, what's the area of the surface? Again, that should sound familiar. And the third one, what's the relative orientation of the magnetic field and the surface? So you can see that all three of these things that mattered in terms of thinking about how much air flows through a window also matter in terms of thinking about this new quantity called the magnetic flux. There are two vectors that we want to think about. The first one we know pretty well at this point. B is the magnetic field vector. The magnitude of it is telling us about the strength of the magnetic field. The direction of it tells about the direction of the magnetic field. But the second vector sitting over here in the picture is new, and it's the area vector. So A here in our picture is the area vector. It has a magnitude that's equal to the area of the surface. So the larger you make this surface, the more area it has, the larger the magnitude of this area vector becomes. The direction is the key detail for our area vector. And notice it is normal to the surface. So here's a situation where we have our surface arranged vertically. So you can think of it as hanging there vertically in the same way you think of a window typically hanging there vertically. And so the area vector is normal to that. It points horizontally in this case. Well, the reason these two things matter is because we can combine them in a way that calculates the magnetic flux by taking advantage of all three of these factors that we know matter. So if I have a constant magnetic field through a flat surface, and those obviously aren't the only options, but they're the ones that we will focus on more than any of the rest in this class, then we can calculate the magnetic flux, which we're going to represent with a capital phi with a subscript b. So phi b here is the magnetic flux. I can calculate that out by saying the magnitude of the magnetic field, the area of the surface, and the cosine of this lowercase phi, which is the angle between B and A. So notice B here is telling me about this first factor. What's the strength of the magnetic field? A is telling me about the second. What's the area of the surface? And cosine phi is telling me about the relative orientation of the magnetic field in the surface, because this angle phi is the angle between the two vectors that matter here, B and A. So let's look at a couple examples. So here again, I've got a picture where I've drawn out my surface. There's the area vector that's normal to the surface. Here's some magnetic field that's penetrating the surface, and so I can see the angle phi sitting there between those two vectors A and B. Well, the first thing to notice, of course, is that the maximum flux occurs when the surface is perpendicular to the direction of the magnetic field. And so this is back to thinking about when the wind was coming up the wall, we didn't get any flux through our window. No air flux came through the window. However, when the wind was coming straight at the window, we maximized the air flux coming through it. This is the same idea, that what you get when you line up your two vectors, the area vector and the magnetic field vector, you get the maximum flux. The angle between these two vectors is 0, cosine of 0 is 1, so you've made the magnetic flux as large as it can be. To be clear, I get the maximum flux when the surface is perpendicular to the direction of the magnetic field. So that's talking about this surface, and notice it is aligned perpendicular to the magnetic field. The normal to the surface, the area vector, is parallel to the magnetic field. So we can describe the relative orientation in one of two ways. We can either talk about the surface itself, or we can talk about the normal to the surface and how those point relative to the magnetic field. And we need to pay attention to which one of those we're being given in the description. A description that tells us that the surface is perpendicular to the field means that we have a maximum amount of flux. A description that tells us that the normal to the surface is parallel to the magnetic field also means that we have a maximum amount of flux. Of course, the opposite occurs, and we get zero flux, the minimum amount of flux, when the surface is parallel to the direction of the magnetic field. So again, here's a situation where my surface is aligned vertically, and so is the magnetic field. So the surface and the magnetic field are parallel to each other, which means the normal to the surface is perpendicular to the magnetic field. So I get zero flux when the surface and the magnetic field are parallel, or when the normal to the surface and the magnetic field are perpendicular. So again, just pay attention to which way the relative orientation is being described in a particular problem. Units of magnetic flux, well, if it's magnitude of B times magnitude of area times cosine of the angle between them, well, B has units of Tesla, area has SI units of meters squared, cosine of phi is just a number, so it's unitless, which means that Tesla meters squared are the units of magnetic flux, and we will rename that and call it Webers. So we will use Weber, capital W, lowercase b, as the SI unit for magnetic flux. Now, knowing how to calculate the magnetic flux is an important first step, but what we're really going to pay attention to is how the magnetic flux changes. And the reason why is because when you change the magnetic flux through some loop, that's going to induce what's known as an electromotive force, an EMF, which will drive a current around the loop. So for starters, what's an EMF? Well, EMF, even though it's labeled as a force, that's clearly mislabeled. Again, it was named before we really knew what we were talking about. So the EMF is not a force, it is an induced potential difference. It's a voltage. So your EMF doesn't have units of newtons, it has units of volts. An EMF is a voltage difference. When you change the magnetic flux through the loop, that creates a potential difference around the loop. That potential difference drives a current in the same way that a battery provides a potential difference in a circuit that drives a current. The difference here is that we're not connecting our loop up to a voltage source like a battery. Instead, what we're doing is we're changing the magnetic flux, which will induce an electromotive force, which will act like a battery and drive a current around the loop for as long as the magnetic flux continues to change. So obviously, if we care about changing the magnetic flux, well, there are three ways that we're going to focus on changing the magnetic flux through a surface in this class. The first one is we're going to change the strength of the magnetic field. So either make the magnetic field stronger, make it weaker. Either way, you've changed the strength of the magnetic field. The second one is we're going to change the area of the surface. Now we can do this a couple of ways. One is we can change the area of the surface itself. So we have some sort of elastic material that our conducting loop is made out of, and so maybe we can stretch it, we can shrink it. So we might be able to talk about situations where we're increasing the size or decreasing the size of the loop itself. The other option is changing the area of the surface through which the magnetic field penetrates. So if I take a loop and either start to move it into or move it out of the magnetic field, then we can think about that as I'm changing the area of the loop through which the magnetic field penetrates, and therefore I'm changing the magnetic flux through the surface of the loop. The third one is I can change the relative orientation of the magnetic field in the surface. So I can take my loop, put it in a field, and then if I start to spin the loop, then what I'm doing is I'm changing the relative orientation of the magnetic field and the surface. So as the surface now spins around, there's going to be times where it lines up with the magnetic field and I get zero flux. There's going to be times where it's perpendicular to the magnetic field and I get maximum flux. It's going to have to go between those 2 points as I continue to turn it. So obviously I can change the relative orientation of the magnetic field in the surface to also change the magnetic flux. So when we change the magnetic flux through some surface in one of these three ways, then what we will do is we will induce an EMF that drives a current around the loop. And why this matters is tied up in what's known as Faraday's law.